basically we'll focus on FP test for knapsack problem. So let's first try to define so what's a knapsack problem. So you have n items, each of them have a weight associated with it and a profit associated with it. Let's say that the profits are P1, P2, Pn, and the corresponding weights are W1, W2, and Wn. So you have given a knapsack as size W. Okay, so you have to pick some of these items so that the weight of the items fits into this. The items that you pick fits into this knapsack, and you want to maximize the profit of the items that you pick. Okay, so this can be formulated as an ILP problem. So I'll just write it as you want to maximize. So for each variable, x of I is a variable that I associated with. This is a Boolean variable. It will take either 0 or 1. X of I is 1 means that you're picking this item. 0 means that you're not picking this item. So if you pick an item, the summation should consider the corresponding profit. So it is x of I into p of I. So if x of I is 1, then you end up adding the profit of it. 0 means that you'll ignore that item. So you want to maximize the total profit that you make, subject to the condition that the total weight of the items that fits into the knapsack is smaller than or equal to size of the knapsack. Right. So you want to pick some items so that weight of the items, total weight of the items that you pick is smaller than or equal to the weight of the knapsack. But you want to pick in such a way that the total profit that you make is maximum. So here xi can be either 1 or 0. That means that you can't, you have to either pick an item or not pick an item. So this is essentially called as the integer knapsack problem. There is a what is known as a fractional knapsack problem, where you allow this x of I to be between 0 and 1. That means that you're allowed to pick fractions. Okay, so this is called fractional knapsack problem. So let me write optimum. So the problem that I am considering now is the 0-1 knapsack problem. So the moment I write optimum, I am talking about the maximum profit that I can make by looking at the optimum solution. So there is also, I'll also use optimum f. So this will indicate that I'm talking about the knapsack problem, which is fractional. Okay. So quick definition: how does these two quantities compare? How does the solution to the fractional knapsack compare with the solution to the integer knapsack? Which is greater? Fractional should be greater. Why is it?
Because you can always take 1.
Yeah.
So, if the fractional solution is less than the 0-1 solution,
yeah,
you could replace the fractional solution with the 0-1 solution. It will still be a valid fractional solution. You can always take xi as only 1, only 0 or 1 without taking a fractional number, and it will be a valid solution.
If you ignore the fractional parts, then it's gone, right? Everything. So because I might end up taking everything as some fractionals, right? So now going from a fractional solution to the integer solution is not clear how to do that.
I meant that.
Yeah.
If there is a situation where the optimal solution for the integer knapsack problem is higher than the fractional knapsack solution.
Yeah. You can just take that solution as a fractional solution, right? Yeah. So what he's saying is that any solution to integer knapsack problem, any feasible solution to that is also a feasible solution to the 0-1 knapsack problem, right? Because here you allow 0 and 1 in the integer one, but you allow more things in the fractional part. So you have more options, the solution space is more for the fractional one, right? If you look at a feasible solution for the 0-1 knapsack, it's also a feasible solution for the fractional one, right? It's because you are just picking endpoints. But the other way around is not true, right? So that's why you have lesser number of constraints when you, so in both the cases you want to maximize this, but here this condition is there plus this condition is there. But if you relax this condition, you have more x of i's which will satisfy this condition. So your maximization, the profits could increase. Okay. So this implies that the fractional one has a value which is greater than this. So this problem is slightly different from the other problems that we discussed in the last 2 days. The main difference here is that this is a maximization problem, but all the other problems that I discussed so far is a minimization problem, right? So I have to worry about what is an approximation factor here. So I have to look at something which is greater than 1 minus c into optimum. So earlier I was looking at a is smaller than or equal to 1 plus something plus blah blah blah. Here so you can just write it as c, right? So a should be greater than sometimes optimum, right? So it should be at least. So if you are trying to maximize the value and the maximum value is 100, you are not going to get a value which is bigger than 100. So the c is going to be a fractional number here. It could be off, right? So that means that I will give a guarantee that my algorithm will give you at least 50 if the optimum is 100, right? So and when I talk about the FP dash here, so what I really mean is that the solution will be at least 1 minus epsilon times the optimum for any epsilon which is greater than 0. Okay, and in order to talk about it, I have to flip everything else that I wrote, right? So the equations are, inequalities are different now. So instead of talking about the lower bound, I have to give a upper bound, right? So it has to say that I will end up saying that this will be at most this much. Okay, so we have a good upper bound for the fractional knapsack. So this is going to be the fractional one is an upper bound for the 0-1 knapsack. So how do you solve the fractional knapsack? So the difference between these two. So the fractional one is solvable in polynomial time just by a greedy algorithm, whereas the 0-1 is an NP-hard problem. Okay. So let's just for completion, let's just look at the solution for how do you get the solution for the fractional one. That's a simple greedy algorithm. So what is a greedy algorithm? Yeah. Consider the profit by W values in the increasing order or decreasing order? Decreasing order, because you want to consider the element which makes most profit first. So consider the elements in the decreasing order of density. Okay, so density is defined as profit by Wi. So then you have certain items, so let's say that A is the solution. Keep adding items into A as long as the total value of the items that you picked is still smaller than or equal to W, right? So you will end up adding A1, A2, A of I. Let's write it as A of I minus 1. And stop the moment when I try to add the ith one. So that is sum of the numbers from W1 plus W2 plus Wi is greater than W. That means that the ith item cannot go into the knapsack. So just you can add the I minus 1th element, the next one element cannot be added. So in that case you take the fraction of the ith item, right? So what fraction do you want to take? Let's call the size of the items that you actually picked is S, which is the sum of the numbers from 1 to I minus 1. So you still have a fraction of W by S left in the knapsack to fill. And what is the fraction that you want to take? W by S. Is that right? Sorry, S by W. So S by W is the fraction that is left in the knapsack that you want to still fill, and size of the item that you can fill is Wi, right? You take this much a fraction of the item. So you are essentially taking S by W fraction of the item. So the weight of the item that you are going to include to the knapsack is this into Wi, right? So S by W is the fraction of the ith item that you need to pick. So weight that is contributing is this, and you get a profit of S by W into P of I. Right? This is the profit that contributes to the objective function. So basically the solution space will look like, so you are picking the first I minus 1 element, and the ith element you are taking a fraction, right? So which is S by W, okay? And you are not going to pick any of the rest of the items. So pick the items as long as the items fits into the knapsack, and when the next item doesn't fit in the knapsack, just pick the fraction which fits into the knapsack. The fraction that fits into the knapsack is S by W, which is a number between 0 and 1, right? So this is the solution to the fractional knapsack problem. So we'll not get into the details why this is correct and things like that. Okay, so now so let's come back to the 0, 1 knapsack, which is also known as integer knapsack. Can I try to do the same thing? Okay. So I try to pick these things. I pick as long as I can pick. I stop here when I can't pick it. So since fractions are not allowed, I will not pick it, right? I will just pick these numbers. So that's a bad solution because you can have two items. So let me write P's and W's. There are two items. One item has profit 1 and weight is also 1. Then there is another item which has profit W minus 1, but weight has W, and the size of the knapsack is W. Okay. So now when you look at the profit by W values, this is still 1, and this has value 1 minus 1 by W, right, which is strictly smaller than 1. So your greedy algorithm for the knapsack 0, 1 knapsack will pick the first item. Now it cannot pick the second item because if you want to pick the second item, the size of the knapsack that you need is W plus 1, so which is not allowed. So if you apply this algorithm, you'll only end up picking the first item, right? So you will end up picking a first item which is value 1. So the total maximum profit that you can make is 1. But the optimum in this case happens to be picking the second item. If you pick the second item, you get a profit of W minus 1. Size of the knapsack is W, so you pick every item. You can pick the second item. So this is W minus 1, right? So your solution is off by a factor of W minus 1. So this example actually not only shows that this simple greedy doesn't work for 0, 1 knapsack, it also tells you that it's not a good approximation factor, right? So if you look at the factor A by optimum, this is very small. This is W minus 1. So given any W, you can always construct a instance of the problem for which the approximation factor is smaller than is as high as W, right? So you lose a factor of W by doing this process, right? So this is very bad. But this simple algorithm, greedy algorithm, can be modified to get a off approximation algorithm, right? In the case of minimization, we looked at numbers which are bigger than 1. For maximization, you are looking at numbers which are between 0 and 1, right? So you can get a off approximation algorithm. The algorithm is as simple. Let's look at this. You look at the fractional solution. I will look at as a fractional solution. I'll just write it as a variable. So you're picking the certain items. The ith item, you're picking a fraction. I'll just write it as a fraction, and you're not picking the other item. So let's say that this is the ith item. Now let's look at this as one solution. This is a solution, let's say x, and I will just consider the next item, right? That's the ith item. That's the solution y. Okay, what is the two solutions that I constructed? One is that I just pick the items that the greedy algorithm actually picks, and just consider the next item in the sequence. The fractional knapsack has picked a fraction of it, but you consider the entire one item, right? Now you consider the profit of these two quantities, profit of x and profit of y. X has a collection of all the I minus 1 items, y is just the ith item. Okay, so pick the max of these two. This looks like I am just trying to construct an example algorithm just to beat the just example that I showed, right? There were just two items. The first item had ratio exactly 1, and the second item was slightly smaller. So what I should have actually done is that I should have ignored the first item, and I should have picked the second item, right? Just to so if I just pick the first item, I make a profit of 1, but the knapsack is not full. If you just pick the second item, in some sense it makes it full and you make more profit. But this technique actually works, and you get a half approximation algorithm for this. So what does it mean? So the solution that I get, if I call it as A is the max of these two solutions, then A will be at least greater than or equal to half the time, half of optimum possible. Okay. So in other words, this is a constant fraction approximation scheme. So you have a half approximation. So let's just try to prove this. So the solution that I get A is certainly greater than or equal to P of x plus P of y divided by 2. Why is this? I am taking average on both sides, and what I have on the left hand side is the max of these two. So max of number A and B should be greater than or equal to the average, right? If I just have any two numbers, any two integers, the max of A comma B should always be greater than or equal to the average. Okay, and the min will be certainly smaller than or equal to the average, right? So we need the max of this. So this I will write it as half of P of x plus P of y. The P of x plus P of y should be, how does it compare with the optimum solution? So P of x picks all this, P of y picks the only this. The profit of x is essentially the profit of all these first I items. The fractional knapsack picks all these items and a fraction of this. Okay, so this should be greater than optimum of the fractional solution. It certainly picks P of x and picks a fraction of the solution y, right? So it is some fraction of not 1. So that's why if you pick the entire item, this doesn't fit into the knapsack. X and y put together doesn't fit into the knapsack, but that's why you're taking a fraction of it. But the total profit that you can make, the moment I write P of x, is the sum of the profits. That's the notation. So the total profit that you make by picking the items in x and y should be greater than or equal to the fractional knapsack. But you know that the fractional knapsack has a solution which is bigger than this optimum knapsack. So this is greater than or equal to half of optimum. So you have a simple greedy algorithm for fractional knapsack. The same algorithm doesn't work well for the 0 and knapsack. Not only that, it also don't give you any good approximation factor. But you can just slightly make one small change to it and get an approximation algorithm, right? Which is good. So any questions so far? Yeah.
So this is an assumption assume that WI is always less than equal to capacity?
Yeah, so let me write that in the next slide. So we have PIs and WIs, and you are also given W. I will assume that WIs are all smaller than or equal to capital W. If this condition is not true, then that cannot be picked, right? If the weight of the item is bigger than the size of the knapsack that I have, but this item will never be picked. Okay. So when I consider the 0-1 knapsack problem, I will assume that every item that you give me can fit into the knapsack. So otherwise, I know that I am not going to pick it, so I am going to not consider those items. Probably this condition is not required for the fractional one, right? Because you can take some fraction of it and still fit into the case. Okay. So to begin with, when I talk about 0-1 knapsack, I'll assume that everything fits in. Okay, so now let's move on to so FP dash. So what is given to me is, let's not talk about FP dash, let's just look at how do you solve the 0-1 knapsack problem. So 0-1 knapsack problem is actually solved by a technique called dynamic programming. Let me just write, so what is dynamic programming? So you have a table and you store something here and you recursively compute this table, right? So let me define what the table is. I want to compute T of I comma j. So I is a index which is a induction on the number of items, and j is a induction on the number of amount of profit that you can make. Okay. So the T of I comma j is defined as minimum size knapsack that is required to make a profit of j using the first I items. So the question, there are two variables here, is one is I, another one is j. I tells me that I am only going to consider the first I items in the given collection. J tells me that I want to make a profit of j, right? See, if you are allowed to consider only the first I items and you want to make a profit of j, what is the minimum size knapsack that is required to make a profit of j, right? So how do you start the, so what is the answer for T of I comma 1? 1 comma j. So if you, yeah, so if you are given the first item and if you want to make a profit of j, when is it possible and when is not possible?
J is the profit of.
So yeah, if j is equal to, so if j is equal to P of 1, then the minimum size knapsack that is required is W1. If that is not the case, then it's not required, it's not possible. So I will write this as infinity. If you want to make exactly profit j, then you have to pick the first item. If you have to pick the first item, then the minimum size knapsack that is required is W1, right? So if you give me any other number, then I can't make that profit, right? So that's it. So now there's an induction. So now, so this is a kind of table. So I know how to, so this will look like all infinity, but one number is this and everything else is this. Now I want to fill this row wise. So initially I was given only one item. If you are given only one item, you know how to solve this problem. Now I will assume that I know how to solve this problem given I minus 1 items, and I want to decide how to solve the problem. If I am given I items, under the assumption that if you give me any I minus 1 items, I know how to solve the problem, and the solution is there in the table. So the trick is very simple here. So when you want to go from solution from I minus 1 to solution to I. So the only additional item that you are considering is the ith item, right? So now let's just stare at the ith item. So if you just stare at the ith item, since I'm talking about a 0-1 knapsack problem, either you pick the solution or you don't pick the solution. So you either, so I'll just write it as tick and cross. This essentially means that you end up picking the ith item. So cross essentially means that you're not picking the ith item. Okay. So if you decided to not to pick the ith item, then you have to make all the profit that you want to make by picking the first I minus 1 items. So the minimum size knapsack that you really need is T of I minus 1 comma j. So if you decide to pick the ith item, your size of the knapsack that you had was W now, the j. But if you decide to pick the ith item, so weight of the ith item is Wi. It occupies a space of Wi in your knapsack. Okay, and you end up making a profit of P of I. Okay, so your objective was to make a profit of j given a size of the knapsack. But if you decide to pick that item, you end up making a profit of P of I, but you occupy a space of Wi. So you need the total amount of space that you need is Wi plus the remaining profit. So this by occupying the Wi space, you actually get a profit of P of I. So you have to make the remaining profit from the I minus 1 items. Okay, and you have to necessarily make a profit of j minus P of I. So here assumption is that it's a 0-1 knapsack, so x of I is either 0, 1, 1. You can't pick an item more than once, right? So that's why it's called 0-1. Either you pick or don't pick, you can't pick more than once. So even if you pick, you can't pick it next time. So remaining profit should be made from the I minus 1 items. Since the total profit that you have to make is j, remaining profit that you have to make is j minus P of I. But you already occupied a space of Wi, so the minimum amount of space that is required is Wi plus T of I minus 1 comma j minus 1. So these are the only two options. You either pick the ith item or you don't pick the ith item. If you happen to pick the ith item, then this is the minimum size knapsack required. And if you don't pick the ith item, then obviously you have to make everything by the I minus 1 items. So you have to pick a solution which requires the minimum knapsack size. So T of I comma j is essentially the mean of these two quantities. So one is T of I comma j, I minus 1 comma j, and Wi plus T of I minus 1 comma j minus P of I. Whichever is minimum, you pick this, right? So you just need two for loops. I is going from 1 to n, so I is going from 2 to n, and j is going from let's say 1 to, what is the maximum profit that you can make? Okay, so you'll have few notations. My capital P is the max of all the P of I's. Okay, so even if you pick all the items, so the sum of the profits that you make will be smaller than or equal to n into P, right? So you can also write it as sum of P of I, but I prefer writing this notation. We'll just take the P as the max of P of I. So the maximum profit that you can make is n into P. Okay, so inside that you just write this loop. If so T of I minus 1 comma j, which is so you know that when you come to this loop, you already computed T of I minus 1 comma j, because when you come to I, T of I comma minus 1, for every j this is already computed. So you compare whether T of I minus 1 comma j is smaller than this quantity. If this is smaller, then you said T of I comma j is equal to T of I minus 1 comma j. Else you said T of I comma j is equal to this one. Okay, so what is the total complexity of this algorithm now? This is theta of n square into p. There are two loops and exactly do this. And in order to store, you need a table of size n cross np. So the total amount of space is also n square into p, right? So you need n square into p space and n square into p time to compute this. Quick questions: how do you so after you fill this in table? So if you look at any entry, so you are essentially going to stare at the last row here because you want to consider all the n items. In each entry here, what this will actually tell you is that if you want to make a profit of this, the entry that is written there is the minimum size of the knapsack that's required. Okay, but what is my problem? So my problem is that I am given a W value. So in all these equations, W has not come into picture. Right, so given the value of W, my problem was what is the maximum profit that I can make, right? So how do you figure that answer from the table that I have? So you want to find minimum. Minimum will be some number here, right? So the minimum number in this minimum size knapsack. If you want to find a minimum number here, it will be very close to. You'll pick an item which is the smallest weight. Yeah. So let's start from the end. Okay, so the end is essentially n into p. So if you want to n into p as a profit, that means that you're picking all the n items. N into p may not be possible. You may not have a infinity there. You start from here, you just keep going to the left hand side because J is essentially telling you what is the profit that I want to make. Okay, so some profits may be possible, but the size of the knapsack that you require to make so much of profit may be greater than W. So in that case, that's not the solution that I need. So what you do is that you start in the last column, last row, and keep walking to the left hand side as long as the size of the knapsack required to make that profit is bigger than the size of the knapsack that you have. You stop the first time when you see a entry here which is smaller than or equal to W. Okay. So what does it imply? If I consider all the n items, if I want to make a profit of J, then the size of the knapsack that I need is smaller than or equal to the size of the knapsack that's given to me. So that particular J is the maximum profit that you can make if you give me a knapsack size W, right? So start with J is equal to n into P. As long as T of n comma J is greater than W, just do J minus minus, and the first time when that loop is out, the particular J that you have is the maximum profit that you can make. So using this table, you can figure out what is the maximum profit that you can make using size of the knapsack, which is W. But what is the problem with this solution? Space and time. So this is a order n square into p, right? So this is not called a polynomial time algorithm. This is called a pseudo polynomial time algorithm because P, what is P? P is the maximum profit, the maximum profit of an item. This could be a very large number. Okay, for example, I might just have 10 numbers, but each of the numbers could be in billions, right? So each of the profit that I write, P of I, could be some 10-digit number. In that case, the maximum is going to be 10-digit number, but the n is only small, right? So this P can be very large compared to n, but when you want to consider something as a polynomial time algorithm, then the running time of the algorithm should be proportional to the size of the input. Okay, even if the number is 10 to the power 10, the size of the input is only 10 digits. Okay, in order to represent the number which is n, I just need log n bits to represent it. So the size of the input for a number is in terms of the number of bits that are required to represent the number. Because if I want to represent a number which is a billion, I don't need a space of billion, right? I just need log of it. So that's precisely what makes this this algorithm what is known as pseudo polynomial. So this is not a polynomial time algorithm, and this problem is NP hard. So if P is very large, then this will take a lot of time. So now P is large, that's the problem. So I want to exploit that now. Okay. So what do I do if P is very large? So this is where we introduce a notion of rounding. Okay. So what is my P? I'll just write it again. This is the max of all the P of i's, and the running time of the algorithm was n square into P. Okay. So what do I do if P is too large? I do something called rounding. So what I write is that I compute P dash. Given P, I compute P dash, which is P of I divided by K. So okay, I have to define what is K now. Okay, I want to divide all the numbers, so all the profits by a K. So if I have to define, so the way I define my table, the P of i's are all integers. I don't allow fractional numbers. Right, so I want to make this also fractional. So what I do is that I'll take floor of it. So if the numbers are all in billions, I want to just divide by 10 to the power 10, right? So that I get 1 or 2, right? The small numbers. Okay. Now what is the K here is the question, right? So my K will depend on the epsilon that you give me, right? So what is our objective? I want to design an algorithm so that it will give me some solution which is greater than or equal to 1 by epsilon times the optimum possible number. So in some sense, this K should depend on this epsilon, and the running time of the algorithm should also depend on the K that I choose. Okay. So let me just see what is the value of K that I want to choose. The value of K that I want to choose is such that, so if I have P into epsilon, this should be equal to K into N. So P is given to you, that's the maximum profit, N is the number of items, K is given to you, epsilon is given to you. So given epsilon, compute your K, which is equal to P into epsilon divided by N. Then divide all the profits by K, and then take the floor of the solution. Now what is the, with this new definition, what will be my capital P dash? So now instead of looking at the original profits, I will look at the rounded profits. I will not do anything to the weights and also the knapsack. I will treat this as the input to my dynamic programming algorithm. So what will be the running time of the algorithm? This will be n square into P dash. Okay, where P dash is the modified rounded off profits. But what is P dash going to be now?
P by floor of P by K.
Floor of P by K, so I will just write it as this is smaller than or equal to, so this theta is there, so I will not write it as floor, right? So theta will take care of all the floor. So this will be P by K, but P by K from this equation is N by K, N by epsilon. Okay. So if I apply dynamic programming technique, so what I get is I get N cube by epsilon as the running time, which is independent of P, which only depends on epsilon. Okay. So let me repeat, what did I do? So I have a dynamic programming solution to the 0-1 abstract problem, but the only problem is that it takes n square into p amount of time and space, where p is the maximum profit in the given collection of items. This is a good algorithm. This solves the problem exactly correctly, optimally. The only problem is what happens if p is large. If the profits are large, then I want to apply a technique called rounding. So what what is rounding? Rounding is essentially dividing by a number k and taking the floor of it. So in order to take a fp dash given epsilon, I define my k to be p epsilon by n. Okay, so if I take my k to be p epsilon by 1, so my p dash, the maximum new profit that I have will be k by p by k. With the choice of k, this is going to be n by epsilon, right? So which is going to be a small number depending on whether epsilon is small or how small is epsilon. Okay, so if I pick this as this thing, the running time of the algorithm is going to be n cube by epsilon. So for the new profits, using an n cube by epsilon algorithm, I know how to compute the optimum solution.
But the solution will not be optimal.
It will not be the optimum with respect to the original problem. Okay, with respect to the modified, rounded off version of the problem, the solution that I get will be optimum. But since I did some rounding, this may not be the optimum for the original problem. Okay, that's precisely where the point is. Just to recap, so how does this technique work? I build an abstract problem. I come to a solution. I pick some items. So after you do dynamic programming, you can do what is known as backtracking. By doing backtracking, you can figure out what are all the items that you need to pick in your collection. Okay. So how do you do that? So in the previous slide, so this is an entry which is smaller than or equal to W. That means that using the first n items, I can make a profit of J by using an abstract of size smaller than or equal to W. So now this entry, because I said T of I comma j is min of T of I minus 1 comma j and some other entry. So this entry should have come from exactly two places, either T of I minus 1 comma j, that's just the above entry, or it should have come from some other entry. If it has come from T of I minus 1, that means that if T of I comma j is equal to T of I minus 1 comma j, that means that I have not picked the ith item, right? So in that case, just update your I to be I minus 1. If that is not equal to this, that means that you have picked the ith item. In that case, you note that you have picked the ith item. Make a collection of j, which will tell you this is the collection of all the items that you are going to pick. Just add into the list. Now you update your I to be I minus 1, j is equal to j minus p of I, and just continue, right? So this technique is called backtracking. Using the backtracking and using this two-dimensional table, you can actually figure out what are all the items that you need to pick in order to make a maximum profit by using an abstract of size W. Okay? That's precisely what I do in this case. There is an instance of the problem where I actually have P of I, W of I, and there is a capital W. I created an instance of the problem, I dash. So the complexity of this algorithm was n square by W. So given in me an epsilon, depending on what is the value of epsilon, I create pi of I dash. So this is basically P of I divided by K. Okay. So Wi will remain same, and the size of the knapsack will also remain the same. I can compute the optimum to I dash, which I'll write it as so let's few notations. Here optimum is the optimum to the original solution. Opt is the actual optimum cost. Optimum maximum profit that you can make use if you pick these items, right? That's what is optimum. Op is actually the set of items that you need to pick in order to make the maximum profit. Opt is actually the maximum value of the profit, right? That's the definition. Let's define this here, which is O dash. Okay. So what is O dash? O dash for the, if I give you these instances, what is the maximum profit that you can make? And so optimum dash is the value for it. So what we have concluded is that if you apply this algorithm and collect, let me call it as that's my algorithm, right? So this runs in order n cube by epsilon, and what I compute the A, this is actually an optimum solution to the rounded version of the knapsack problem, right? So after I rounded the profits, I have a new profits, I apply dynamic programming, I get optimum solution because dynamic programming actually gives the optimum. But the problem here is that this may not be the optimum to the original instance of the PFI. So I solve this problem and I just take this A, the items that you pick, I report that as the solution to the original set. The first thing that you have to worry is see why this is a feasible solution, why all these items actually fits into the knapsack. That's easy to see because I have not modified the weights, right? What I modified is only the profits. So if I retain the same solution for the original knapsack, all of them actually fits into the knapsack. Okay, so the feasibility is not an issue. So now I want to show that this may not be optimum, but I get something which is very close to the optimum. Okay, rest of the lecture is about just writing some equations which will tell you that this is very close to the optimum. Yeah. O is optimum to the actual problem. So O dash is the rounded variant of the knapsack problem. Rounded, essentially I am only rounding the profits. Okay. So A is the solution that I get by dynamic programming, right? So dynamic programming solves it optimally, so A is actually equal to optimum dash. So now let's look at, so is the solution clear, is the algorithm clear? I did rounding, with the rounded variance I pick some items which is the optimum with respect to the rounded variant. Now I want to know this is the final answer to my actual instance of the problem, which is I. So now let's look at total profit of the item A, which are picked in A. So how does it define? This is defined as P of I, where the i's are in A. Okay. So let me write two more equations depending on so what I wrote here. So how does P of I dash compare with P of I by K? Yeah, which is smaller? It's a floor, so this will be smaller than this, but this will be greater than P of I by K minus 1. Right, so if it's 2.5, I am making it as 2, so this will be between 1.5 and 2.5. So if I multiply K on both sides, what I am going to get? So P of I minus K is smaller than or equal to P of I dash into K smaller than or equal to P of I. So have P of I here. So this is greater than or equal to K summation of P of I dash into K, where I actually belongs to A. How did I get this equation? You have to just look at this part. P of I is greater than or equal to P of I dash into K. So, but A is an optimum to I dash, but somehow I want to compare it with the optimum. Solution is A. Okay. So now let me write an equation here. Sum of so let me write here. Sum of P of I dash, where I is in A, and let's also look at P of I where I is in O. I dash. How does these two quantities compare? Just by definition. So let me repeat, A is the solution which is an optimum solution to the rounded variant of the problem. What is O? O is the set of items that you need to pick so that the original knapsack, you can make maximum profit. So now, what is that I am looking at? Both sides, I am looking at rounded variance of the profit sum. Here the summation is taken over all the elements in the solution A, which is given by the dynamic programming. This is the summation over all profits, rounded variance of the profits with respect to the optimum here. This is the collection of elements that you are going to pick. Just look at the rounded values of it, right? How does these two quantities compare? Yeah. So here there is a P dash, there is a P dash here. This is over the set A, this is over the set optimum, but optimum with respect to the original set. How does these two compare? Which is less? I should write a less than here. Why? So what is A? A is equal to, I solve the optimum solution for the rounded variant of the problem. So as long as you consider P I dashes, this is the maximum profit that you can make. Right? So what is O? If you look at the different problem, if you pick these items, this is the maximum profit that you can make. With respect to P of I's, O is the solution which will give you the maximum profit. With respect to P of I dashes, A is the solution which will give you the maximum profit. Now if you look at the elements that are there in the optimum, if I look at the elements which are there in the rounded variant and just sum up their rounded values, which one should be greater? Left hand side should be greater, right? So this is because as long as you consider the values in the rounded variant, A is the optimum which is computed by greedy. As long as Pi dash is considered, O is not an optimum, it's just a feasible solution. But if you write P of I's here, the O will give you a bigger value because that's the optimum. Okay, so I can write that this is greater than or equal to, K is a common term here which is independent of the P of I's here. So I can write that this is greater than or equal to K into P of I dash into I which is in O. So K into P of I dash, I want to use the other side of the equation now. So this is greater than or equal to summation of I in O. So what is the other side of the equation? So this K is a P of K into dash will be summation of P of I minus K. So this I will write it as greater than or equal to the summation of P of I, where I is in O, minus K into the number of elements in O. Right? So this is summation over the set O. So the I is retained as it is, but on the other side you have a K there. So you have to count K the number of times the summation is taken over, which is O. But how many elements are there in O? How does the number of elements in O compare with N? So this is smaller than or equal to N because you can't pick all the N items. Okay? And this is actually, what is this quantity is actually equal to? So this quantity is actually the optimum, that's my definition. So what is optimum? Optimum is the maximum profit that you can make. So the sum of the items, O is the solution which gives you. So if you just sum of the items in this collection, what you get is optimum. Minus K into N. K into N, this is I am essentially using is that optimum is smaller than or equal to N. So if you do negation, then this will be greater than or equal to this. Okay, I have not used the choice of epsilon till now, but I used K here. So now I want to replace K with epsilon, right? So otherwise the running time was N cube by epsilon, but the quality of the solution also should depend on epsilon. Right now I have N, K. So I want to replace N into K by epsilon, right? So, so if I look at the previous this thing, so what was the choice for K? So So n into k is p epsilon. Okay. So this is actually equal to optimum minus p into epsilon. Okay. This I can write it as greater than or equal to optimum minus optimum into epsilon. So why is that? So the optimum is greater than or equal to p. That's what I am using here. So the minus p will be smaller than so minus p in that case will be greater than or equal to minus optimum, right? Why is this condition true? So what is p? P is the maximum profit, and I said that every item has a weight which is smaller than W, right? This is coming from that. So weight of every item is smaller than W. So if you look at each of the individual items and put into the knapsack, that's a feasible solution, right? So the optimum that you can make will certainly be bigger than the maximum that you can make. So the optimum is greater than the solution which has contained just one, which is the maximum. So you, in fact what this actually means that you just look at the item which has the maximum profit. Since its weight is smaller than W, you can always put it to the knapsack. So the optimum solution will have a value which is certainly bigger than that. So if I do that, then the minus p is greater than minus optimum. So this is actually equal to 1 minus epsilon into the optimum. So the solution that I have, which is A, has a value which is greater than or equal to 1 minus epsilon times the optimum. So you can choose your epsilon to be very small. So if you choose your epsilon to be very small, then the running time will be n square by epsilon. So, but if you look at this k, right? So if epsilon is very small, then your k will be very small. So you are going to divide this number by a very small number. So the profits are going to go up. So if you have profits more than bigger profits, then your running time of the algorithm actually depends on the maximum profit. That's bad, right? So that's precisely the result here. So what is the summary now? So what's the algorithm for dynamic programming FP test for the 01 knapsack? You start with the original problem, do the rounding. When you do the rounding, you round only on the profits, not on the weights. So once you did the rounding is essentially dividing by a k, but the k is the function of maximum profit that you have, epsilon and n. Once you did this, then the profits are relatively smaller given your epsilon is reasonable number. Once you do this, then you can apply the dp solution and get a solution in n cube by epsilon, which is independent of the size of the profits. It only depends on epsilon, right? So once you go from here to here, the running time of the algorithm will depend only on epsilon, not on the original instance of the problem. Now you know for the new profits, you know how to exactly compute the optimum solution. Compute that optimum solution. Just report as that as the solution to the original problem. Okay. So because of rounding that you did, you may not get the optimum to the original problem. But what the proof on the right hand side shows that you are not going to be too far away from the solution to the optimum to the original problem. The solution is just solve the apply dp and solve the rounded variant of the problem and report the solution. That's it. Any questions? Okay. So the solution that you have is P of A, which is greater than or equal to 1 minus epsilon times the optimum. Yeah.
When we have to go for rounding and
so it depends on what is the value of P, maximum value of P. Okay. So your running time is n square into P, right? So it depends on what is the value of p. If p is smaller than 100, then if n is also 100, then you can solve the problem in polynomial time, right? So you don't need approximation algorithm. But if n is 10 but p is all in millions, then these are large numbers. So if you want to apply this technique, it's going to take more space and more time. That's where you do the rounding, right? So when you do the rounding, you can divide by any k, so that the numbers that you have is smaller and it's reasonable. But so what you divide by the k that is the one which is defining the rounding here. Depending on the value of k, the algorithm will decide how close it will return an answer which is close to the optimum, right? So if k is very small, then the numbers are still going to be bigger, so you will take more time to compute the solution. But if k is small, then you are likely to go very close to the optimum. The k is proportional to epsilon in this case, okay? So if k is small, then the numbers are going to be bigger, so you will get a solution which is very close to the optimum. But if you choose a k which is very large, then the numbers are all going to be small. So if the numbers are going to be small, then the dynamic programming table is also going to be small. But once you solve the dynamic programming solution, you may not get very close to the optimum, right? So there is a trade-off. Yeah. So for NP hard problem, probably this is the best that you can do, because given any epsilon, I can get as close as we want to the optimum, and you are very close to epsilon, but your running time will only appear on the constants, right? It's n cubed by epsilon, not n to the power 1 by epsilon and things like that, right? So probably for an NP hard problem, F8 is probably the best that you can expect. So if no questions, let's go back to the hitting set problem and try to see what is the connection to the set cover problem that I defined yesterday. So let's just look at set cover problem. In the set cover problem, you have an universal set. I'll just write it as x1, x2, x of n. Then you have s1, s of n. These are all subsets of U. The set cover is essentially, I'll write as a C, is a, you have to pick some of these subsets so that the union of the, so union of S of i's where I is in the set cover is actually equal to U. Whereas the hitting set problem was the same, so you still have some of these things, but what you wanted in a hitting set problem is that you wanted a set H, the smallest size set H, such that when you take the intersection with S of I, for every set this is non-empty set, right? So in other words, you pick at least one element from each of the sets, right? So this set is, you can look at as a representative for different S of i's could be, so X of I could be people, your sets are essentially your, so what is the best example, WhatsApp group. Now you want to pick one element, enough people so that you can send messages with the assumption that each of them will forward to the respective groups, right? So you want to pick not too many people, but small number of people, so that you picked at least one person from each group, right? That's what is the hitting set problem. There's a neat relationship between these two problems. So what I do is that I try to construct what is known as a kind of bipartite graph, where I have one side all the elements x1, x2, x of n. So what I have on the other side is the all the sets that I have, right? So this is S1, S2, S of M. What I have on the left hand side, all the elements. What I have on the right hand side, all the groups. In other words, these are the elements in the universal set. What I have on the right hand side is all the, every vertex I have a set. So when do I connect an element on the left hand side to the right hand side? Yeah? If this element is in this set, there is a connection here. Okay? If this element is there, then whichever elements which are there, I will just connect that. Okay, what is the set cover problem now? Yeah, just pick some vertices on the right hand side. Okay, so that when you look at the edges which are incident on it, you should cover every vertex on the left hand side. Right? So these are sets, you don't want to consider all of them, you just want to pick some of them. Then when you pick some of them, you just look at all the edges which are incident on it. You should cover everything on the left hand side. So what is the heating set problem? Heating set problem is the dual of it. Right? I stand on this side. I want to pick some vertices on this side, so that when you look at the edges which are incident on it, you should cover everything on the right hand side. Right, that's all. So these two problems should be same then, right? So if you look at as a bipartite graph, and this is on the left hand side, there is on the right hand side. So one problem is essentially you have to pick some vertices on the right hand side, so that if you just restrict the subgraph to the vertices on the right hand side, it cover everything on the left hand side. The other problem is that you have to pick something on the left hand side, so that when you look at the edges which are outgoing from these vertices, you should cover everything on the right hand side. So pictorially, if you can solve one problem, we can just find the dual of it and solve the other problem. Right? So mathematically, how do I do it? How do I go from the set cover problem to the heating set problem? In other words, I have the algorithm for the set cover problem. Given an instance of the heating set problem, I should be able to translate that into a instance of a set cover problem. Once I do that, I have an algorithm, I just call it. Right? Whatever is the solution, I should be able to go back to the solution there. What is the translation? How do I go from set cover to heating set? Okay, so this diagram should help you. So you should be able to flip the sides and then tell me what is the sides, what is the elements. Set is the element there. Okay, when you go here, every set here becomes an element, right? So instead of writing capital S, I'll just denote them as a small s. These are the elements in the universal collection. What are the sets now? So I'll write it as the capital S1 here. The small s1 will essentially map it to the corresponding sets here. So I'll write x1 here, which is a set here. So what is the set now? Sets are elements. If sets are elements, what are the sets now? Yeah. So there will be n sets. So how do you define x of I now? It's a collection of all s of j such that small of x of I is a part of x of j. Okay, that's all. But when you implement the algorithm, you don't have to do all this, right? So all these equations are written to just to understand what this greedy algorithm actually implies now, right? So eventually I want to apply the greedy algorithm on the set cover after this conversion, right? So what is the greedy algorithm on the set cover? Just pick the maximum set which covers the maximum number of uncovered elements, right? That's what is this algorithm for the set cover problem. I started with the heating set problem. I converted into a set cover problem. Now I want to apply this particular algorithm. Now I want to see what is that algorithm translate to in terms of the heating set that I, right? So you, sorry, I should have done the, so this mapping is fine. So the conversion should have been that I want to solve the heating set problem. I converted into the set cover problem. The conversion is essentially what is written here. Now I want to apply the greedy algorithm on the set cover problem. The greedy algorithm on the set cover problem is essentially pick a set which covers most of the uncovered elements. Okay. If I want to implement this way, then I have to explicitly write down these sets, go from one set of instance from I to I dash, and then call the set cover problem. For that you have to do all these things, right? So I don't want to do all these things, but I want to just interpret what this algorithm that is applied on the new set of instances that I created. So what does it imply on the original set? Right, so instead of applying the, pick the most uncovered elements into the collection on the set cover, for which I need to create I dash. Can I interpret that algorithm on I itself? So what is what does that indicate on the original set problem, original heating set problem? Yeah. So that follows from this equation. Putting it in a different way, you want to pick a set which is part of most of the sets which are uncovered now, right? In other words, you want to pick an element here. So you pick one element, it covers few edges, just delete all of them. Okay? If you end up picking this, any edge which is incident on it, all the vertices on the right hand side, just delete them. Now you pick an edge here which has the maximum degree, right? In terms of graph theory, in terms of bipartite thing, if you want to solve the set cover problem, you have to start on the right hand side. Your algorithm says pick the vertex which has the maximum degree. Once you pick that, delete that vertex from here and delete all the edges which are incident on it. Now you just work on the rest of the graph, same algorithm, right? Pick the maximum degree vertex, include that in your solution, delete that vertex and also all the edges which are incident on it. When a vertex becomes isolated, you just delete that also, right? All the edges and also all the vertices which are incident on it, you want to delete everything, right? So when you want to come, so that's the algorithm for solving the problem set cover. But if I want to do that on the heating set, I want to start on the right hand side, pick an element of maximum degree, include that in the heating set, delete this vertex and delete all the vertices on the right hand side which are incident on it. Okay, repeat that process. Okay, so this will essentially translate to pick a vertex which is part of most of the sets, and then when you come back next time, you pick a set which is part of the most of the sets which is not considered earlier, right? That's what is the algorithm turns out to be, and the same proof works from this diagram, which will give a order log n algorithm for the heating set. Yeah.
Sir, if we consider in the heating set problem, if we consider the sets are of two sides, then is it same as vertices?
Sets are of size 2.
Yeah, that means sets can have only two elements.
If the sets can have only 2 elements, it's essentially saying that every vertex has a degree 2 on the left hand side.
No, I'm not considering in terms of hypothesis.
This helps us to understand the problem in a easier way, right? So does that really help us?
I'm thinking if it will be the vertex.
Is it going to be the vertex cover problem?
That is the case, this is leading position from picking the maximum degree.
So what she is saying is that
the elements x1, xi's are within the vertices and the sets represent two tuples. Set has a coordinator 2.
okay. So what she is saying is that so you have so these sets are essentially your edges. Yeah. So you have u comma v, you have u comma v, you have yeah. So u1 comma v1, u2 comma so something like that. These are the sets. Your this thing is v1, v2, vn. Your collection of edges are essentially your sets. So now what is the heating set problems? I want to find a vortex cover which is a heating set such that if you give me any set, there should be one vertex here which is incident on it. That's essentially the same as saying if you give me any edge, there will be at least one edge which is incident on it, right? So the heating set problem now, if you look at this way, is exactly the vortex cover problem, right? The vortex cover problem is exactly the heating set problem. Now if I apply greedy, so what is guaranteed? Yeah, order log n algorithm. Okay, does that contradict anything on what we have studied? We have an algorithm for the set cover, the vortex cover, which is a 2 approximation algorithm. Okay, but here if you look at this problem as a heating set problem and solve this problem, you get a order log n. Okay, so the vortex cover is a special case of the heating set problem. Okay, but if you just want to solve the vortex cover problem, there is a fast algorithm which is a constant time algorithm. But here if you look at this problem as this, then you solve this, you get a order log n. Okay, there is no contradiction. Okay, heating set is a generalization of the vortex cover problem. But if you want to solve the vortex cover problem, you can apply this technique. This essentially same as saying pick the maximum degree vertex and do all this. But so what this, if you pick the maximum degree vertex and do all this, you only get a order log n guarantee, right? So if you want a 2 approximation stuff, you have to do different. Did everybody follow this? Okay. We have seen an algorithm for the vortex cover. We have seen an algorithm for heating set. So what she is actually concluding is that this vortex cover problem can be looked at as a special case of heating set problem, right? So why is this a special case? This is the construction. You look at your set of vortices in the graph as your universal set. Set of edges is your actually the edges. Now the heating set problem is to essentially find a vortex cover with the minimum size. Okay. Now this problem can be reduced thought of as a heating set problem and solve it, but if you do that, then you only guarantee order log n. So if you want to study the specific variant of this heating set problem, which is a vortex cover problem, there is an alternative version algorithm which is a different algorithm than what we described, which guarantees a 2 approximation algorithm. Right? Here the sets are all specific. Every set has only 2 elements in it, but in general it can have more, right? So this solves a general variant of the problem. You had a question? Yeah, understood? Okay. Yeah, you have a question? Repeat, no? Just look at, you have a graph, I am just visualizing the vortex cover problem has a heating set problem, right? So what do I have? I have a graph V comma E, that's what is given to me. I want to look at it as a heating set problem. I have to define what is the universal set, what are the sets. Universal set is essentially the set of all vortices, okay? So what is the collection of sets? Every edge will map to a set. Okay, what is the mapping? You just look at the endpoints, those are the elements which are there in the set. Okay, Now what is the heating set now? You want to find some of the elements in the universal set with minimum size, so that any set that you take, it intersects. Which essentially same as saying that what is the set here? It's an edge. When you take an edge, one of the endpoints should be there in your heating set, which is essentially the definition of a vertex cover. Okay? The problem is, this essentially says that a vertex cover problem can be looked at as a heating set problem. Now you apply the algorithm for heating set problem, that is pick the maximum degree vertex and then repeat the process. This guarantees a order log n algorithm. Okay, but if you are interested in solving the special case of this heating set problem, you don't do this. You have a other greedy algorithm which gives you a 2 approximation scheme. That's all. So vertex cover is a special case of heating set. That's all we are saying. For the general version, we only have order log n algorithm. For a special case, we have a 2 approximation scheme. Can I make the statement? So that depends on what is the meaning of hardness, right? So if you look at in terms of Turing computability, both are NP hard. So one is polyreducible to the other one, which implies that if you can solve one, you can also solve the other one in polynomial time, right? So in that sense, both the problems are equally hard. But if you look at the hardness as designing an algorithm which gives you an approximation algorithm factor, right? So how close can you get to the optimum in polynomial time? If that is the definition, then one is easier than the other, right? Because we don't have anything faster than order log n for the set cover, but we have a 2 approximation scheme for the other one. In the knapsack, we have a FP dash, right? If that is the notion, then the knapsack is much easier than vertex cover, which is much easier than the set cover, right? And if you want to solve the general TSP, that's the hardest one, right? You can't solve it reasonable approximation.